Let's talk about dipole now. Okay, so if you remember, dipole is a very simple concept. It simply says that you'll be basically having two charges, right? If you're basically considering something like a dipole, you just have two charges, right? That's plus q. Okay, there's one charge and this here, and then there is minus q. Okay, and these two charges are opposite in polarity but equal in dimension, and we can actually have a straight line joining these two charges, and the length of this is nothing but, for convenience we say, 2 times of L. Let's say that's the length for the dipole. Okay, now we know that a dipole can have two positions. One position will be on the axial line. Okay, so let's say we have got a point P which lies on the axial line. It lies on the axis. Okay, and whenever we say what is the distance from the axial line, the distance in case of a dipole is always measured from the center. This concept has to be clear. Okay, the distance is always measured from the center, so that means the distance from the center of the dipole to the point P, let's say, is x. Okay, let's say is nothing but x. Okay, so now we know what are the distance of charges minus q and plus q from the dipole. Okay, and this is my axial line. The question is, find the potential. Sometimes they do write it as electric potential at P on the axial line. Okay, so diagram might not be given, it just might be asked that you have to find out what is the potential P on the axial line. So this is just the application of the potential formula. Okay, so we are getting two questions. Let's say we want to find out potential and electric field. Electric field we have already seen before, but anyway, uh, let's check for the potential right now. Okay, so the first thing first, we should know what is the formula for potential. We know potential is kq by r. Never mix up these two, very important. Many a time student do mix up this, and because of which the entire derivation will become wrong. Electric field is kq by r square. Remember this. Okay, electric field is a vector quantity, so it will basically have a direction, but this is a scalar quantity. Okay, so we're going to use this formula. Okay, so you can see that if we check the potential at this point P, the potential at point P, it will more or less be because of the potential which happens because of plus q and the potential which happens because of minus q. If this concept is clear that we can add up the potential without thinking about the direction, then you will be able to solve most of the problems in potential energy. Okay, so let's write down each of these. So V of q plus q is nothing but kq divided by r. R is the distance, so this is q, this is p, so it's from the bisecting angle, so it is L. This distance is L, so it is L plus x, right? So at the bottom we can write it down as L plus x. Similarly, we can write it for V minus q. Now it's a scalar, it's not a vector, so we have to consider the sign of the charge. If it was a vector, we'll consider the direction and won't consider the sign while doing our calculation, but if it's a scalar, we have to consider the sign. Keep these thumb rules clear. So it will be minus of kq divided by, now this is entire, this is L, and this entire distance is x, so I'll take x and subtract L. I'll find out this distance, so that means this distance that we have is L minus x. Okay, so this is L minus x and L plus x. Okay, so what I'm going to do is I'm going to say that the distance between these two dipoles are very small compared to the distance x. Okay, so what I'm going to do is, this is actually something which is practical and important as well. This distance x will always be greater than the distance between the dipole, or half the distance, x minus l. So let me just write it down as x minus l. Okay, So dipole is within a very short distance. We have to make it clear. So what we can do is we can find out what is the potential at point P. I can simply write it down as Vp is equal to kq, that's common, and within bracket I can write it down as 1 divided by x plus L minus, because there is a minus here, and 1 divided by x minus L. So I can simply write it down as kq, give a bracket. This is a plus b into a minus b is a square minus b square. So I'll write it down as x square minus L square, and on top it would be x minus L minus x plus L. So if I open the bracket, minus x minus L, just LCM. So it can cancel this out. So I will have it as minus 2, right? This is x minus L and this is minus L, that's fine. So minus of 2kq into L. Okay, so we can take it like this, divided by x square minus L square. Okay, so that means that okay, that means this is clear. I hope you remember. 2L is the distance between the dipole and q is the charge. That means this is nothing but dipole moment. So if you remember, P is the dipole moment, is nothing but the distance between the dipole into the charge. So this is my dipole moment. So I can write it down as minus kp divided by x square minus L square. This is the potential at point P because of the dipole. Okay, so this is the potential due to the dipole. We can simply do it this way and we can find out the potential. It's simple addition, there is no issues with this, but we have to consider this condition, that if this length that we are talking about, that means the distance between the two dipole is very small compared to x. Okay, let me take an example. The length between the dipole may be in millimeters. Okay, L might be in millimeters, but this distance that we are talking about might be in meters. So millimeters, 10 to the power minus 3, this is in 1 meter. So that means this is very small compared to this, and that is actually the case. A dipole cannot be two charges of same magnitude, opposite polarity, which are separated by a very large distance. That doesn't constitute a dipole. Okay, so if this L is much less than x, I can write down the dipole moment as minus kp divided by x square. Okay, x is large, so I can take it like this. Okay, so what is interesting here is that, okay, if you go to our previous cases, if you're just considering a ring of charge or a single charge, it is inversely proportional to r. Okay, but then if we are basically considering not r, if you consider this case kq divided by root over r square by x square, if r is small, x is large, it will be kq by x. Okay, if this r is very small, but when we are talking about a dipole, it is inversely proportional to x square. So this is my potential due to a dipole on the axial line. Okay, so I'll write it down as axis, axial line. Okay, so that's the first case for dipole, and in a similar way we can also find out the electric field. Okay, so electric field, what happens is you're basically going to consider it as a vector. Okay, so it will basically have some direction involved. So what happens is, if you actually want to find out the electric field for the same dipole, not the magnetic field, you want to find out the electric field, not the potential, rather. You have not yet reached magnetic field. If you want to find out the electric field, this is valid for all kinds of problems. You have to consider the vector here. This is plus q, this is minus q. First draw your diagrams clearly, that's very important. So what I'm going to do is, I'm going to join these. Okay, and then I am going to consider a point P. Okay. Now if you want to find out the electric field, you have to imagine that you are placing a test charge Q here, okay, plus Q naught, which does not have a field of its own, and see, is it getting attracted or repelled. So if it is a negative charge, it's a positive charge, so this test charge will get in this direction. Let's say the electric field because of this is E1, and the electric field because of this is E2. So that means if it is getting attracted, if you put a positive charge here, it will get attracted, so the field direction is this direction, so this is my E2. On the other hand, if I consider it because of the positive charge, this is positive, that is positive, it gets repelled, it will be E1. Okay, what will be the direction of the resultant field? That's quite simple, because we know that E is equal to kq by r square. In both the cases, if we just consider the magnitude, in both the cases the charges are the same, the only thing is the distance. So if you see this, if the distance is large, the intensity is less. Okay, the distance is large, the intensity is going to be less for the electric field. Now in this case, this distance is large and this distance is small. Okay, so the smaller distance, the intensity will be more. Okay, so this distance is small, the intensity is more, so that the resultant field that we have will be in this direction. So direction is not an issue, we already know what will be the direction by looking into the geometry and understanding the dynamics here, right, of the distance. Okay, now let's find out what are the two electric fields that we have. Let's find out what is E1. So E1 is nothing but K Q charge, okay, divided by distance square. So E1 means because of this, so let's say the dipole is of length 2L, same logic, and this point P, okay, is at a distance x from the center. So that means from here it will be nothing but half distance, which is L, this is L plus x. So I can simply write it down as L plus x. Okay, that's the direction. Okay, and for E2, since it's a vector, we are already considering the direction here. One is opposite to other, so I don't need to consider the sign. So I'm not going to write down minus q here. I'm just going to write down only the magnitude kq divided by. Now if you look into the distance, this is L and this distance is total is x, so it is x minus L. Okay, same logic again, x will be larger, so x minus L. Okay, now if you want to find out the resultant field, E resultant, we know that this electric field and these electric fields are opposite to each other, and obviously whichever is larger will come in front. So x minus L, x plus L, x minus L is larger, so I can simply write it down as E2 minus E1. E2 is larger because the denominator is smaller. Okay, so let's try doing this simplification here. So if we take this, this is kq, and if I'm squaring it, let me just keep it like this, x minus L whole square and x plus L whole square. Let's see how we can simplify this. So this will be x plus L whole square, x plus L whole square will be nothing but x square plus L square plus 2xn, right? And if I want to take it for the other part on this side, it would be minus x minus L whole square, so it would be x square plus L square minus 2xn. Okay, now I think we should be able to get the right answer. So this would be nothing but kq, give a bracket, this is a minus b into a plus b whole square, we can write it down. So I can simply write it down as x square minus L square whole square, and then this would be nothing but, if you open the bracket, this is x square minus x square, this is L square minus L square, 2xl minus minus plus plus 2xl, so it will become 4xl. Okay, so in that way what we are going to get is kq into 4xl. So that means I can simply write it down as 2 times of k into q into 2xl. Okay, So we've got this result. Okay, so we are getting an x which actually survives on the numerator. So I can write it down as x square minus l square whole square. So that means I can take q to l and take it to be the dipole moment. So I can write it down as 2k dipole moment x divided by x square minus l square whole square, right? So therefore what we can see is that the resultant electric field is this particular result. So I can simply write it down as 2 kpx divided by x square minus l square whole square. Okay, this is my resultant electric field. It's quite different from the potential, but in case this x is very large compared to L, we can write down this ER is equal to 2 k p x divided by L. L is small, x is large, so you can simply write it down to be x to the power 4. That's cancelled, it becomes cubed, so I can write it down as 2 kp by x cubed. This is my electric field, which is more or less practical in nature. Okay, and what was my potential that I found out? It was nothing but minus of kp divided by x, right? So minus of kp divided by x square, sorry, divided by x square. So you see there is a lot of difference between the electric field and the potential. And in case a graph is given, you will see that ER is proportional to 1 by x cubed, but EP or V is proportional to 1 by x square. So that means the slope of this will be larger compared to this. So you can think about the graph and more or less solve a lot of problems. Okay, this is minus, it can become plus. It's just simply you have to take the point P not on this side but on this side. If you take P on this side, it will become plus. Okay, I'm taking P on this side, so it is becoming minus. Okay, it just depends which polarity you are actually considering, but the maths will more or less remain the same. So if it is to be derived, you're supposed to derive it like this. Okay, so we have found out what is the potential on the axial line for the dipole, and I've also found out what is the electric field for the axial line of the dipole. Okay, and you can see and compare both these cases. Just make sure don't make the mistake I made just now. uh, Electric field is r square, so if you take a square of that, potential is not square, so we just have to take the the linear variable. The technique, that's very important. So let's now talk about the equatorial line. Okay, equatorial point. Okay, for the dipole obviously. Okay, and we are interested to find out the electric field and the potential. Okay, so we're going to do the same thing now, but we are going to do it on the equatorial line. Understand the concept, you can solve any kind of problem, it should not be very difficult. Okay, so let's take up this equatorial line. So we have got two charges at the 2 points, and the equatorial line will be somewhere on the perpendicular bisector. Okay, there will be a distance L, and this will also be a distance L. Okay, this is my equatorial line. What we can do is we can join these points. This will obviously form an equilateral triangle. Okay, it will form an equilateral triangle, so we can join these lines here. Okay, and what we have here is we have got, let's say, a charge of plus q on this side and a charge of minus q on this side. What I'm interested is to find out what is the potential at point P. Now the best part about potential is it's a scalar quantity, so you have to just simply add up, right? Add up the potential, and that's it. You can find out what is the potential on the equatorial line. Okay, so you can simply do that, and let's say this distance that we have is x. The distance from the point P to the dipole is x. Okay, so obviously this distance is nothing but x square plus l square, and this distance is also x square plus L square. Okay, these are the two distances. Okay, so that means the potential at point P will be, because of the two charges, that's because of minus q plus the potential because of plus q. Note, both the distances are same. Okay, so we know our potential formula. Keep this as the base, q kq divided by r, the distance. So for minus q, since it's a scalar, I'll take minus sign. It will be minus kq divided by root over x square plus L square, and plus, for plus q it will be kq divided by the distance will remain as x square plus L square. Now this is nothing but 0. Okay, this is a very interesting observation, because if you look into the equatorial point, the potential will be become 0. Equal and opposite, they cancel out each other, but that does not happen for the electric field. Okay, but here I'd also like to give you a short concept on equipotential surface. So I want to know the equipotential surface. What does it mean? So I hope the term is clear, because it's not very complicated. Equipotential means the potential is same at every point on a particular surface. Okay, the potential is same. It may not be 0, but I'll give you a simple example. Let's say we are basically having a charge plus q on this side, and we have got a charge of minus q on this side. Okay, and in between we are basically having a thin sheet. Let's say this is a thin sheet. Imagine it in three-dimensional picture. This is a thin sheet. Okay, so if you want to find out the potential at any point on this sheet, maybe here, maybe here, here, so on, and all these things are at equidistance from this side and this side. This is at equal distances from this also, from this also. So that means whatever is the potential on this point, because of this, at this point it will be the same but opposite in magnitude. That means for this entire sheet, you consider any point, at all these points the potential is going to be 0 or same. In this case, obviously it's a special case where the potential remains the same. We have seen that it is 0. 0 is a special case. So this is a equipotential surface, means equal potential. So this example that we have taken for a dipole on the equatorial line, if we are actually drawing a surface on this equatorial line, we can actually see that the potential will remain 0 at all these points on the equatorial line. Let it be here, let it be here, let it be here, exactly at a point in between the two dipoles. This is always going to be 0. You go at the bottom or go to the top. If the distance is same, the potential is going to remain the more or less the same. So that's very important. Okay, so that's the idea behind equipotential surface, which is also there in the syllabus. Okay, important. uh, let's just quickly do it for the electric field on the equipotential surface. I think we have already drawn the diagram for that. So maybe we can actually take up that diagram and use it, okay, rather than drawing it again. So let's take it. Yeah, this was our equatorial line, okay, and equatorial point. And if we do our calculations, we're going to observe that this is more or less going to be this value. Okay, let me see if I've calculated this. Yes, I think we have already done our calculations. So if we talk about the electric field on the equatorial line, we can see that this is plus q, this is minus q. So that means if we look here at this particular point, because of plus q, if you put a test charge plus q here, the electric field will be away. So this is my direction of the electric field. It will have two components, the horizontal component, that is the cos theta component, and the vertical component, that is the sin theta component. This is angle theta, so this is also angle theta. So this is cos theta component, this is sin theta component. On the other hand, if I consider it because of minus q, I will have the electric field downwards. So this will be theta, so that will be cos theta component, and downwards will be the sin theta component. But both are at equal distance, so that means the sin component will more or less get cancelled and the cos component will add up. So that means the resultant field at the equatorial point would be eq cos theta plus e minus q of cos theta. Cos theta we can see it from the geometry, is nothing but the base, which is L, divided by the hypotenuse, which is root over of r square plus L square. Okay, so I'm not going to repeat it, because you can use the same formula as potential, but only remember this is a square in the denominator. So I can simply write it down as you know uh, the electric field. Okay, the electric field is kq divided by root over of r square plus L square. These two you add up, you get a 2, so twice kq of this into cos theta. Cos theta is L by root over r square plus r square, and you can take it and you'll see that you're going to get it in terms of the uh, you know uh, dipole moment. So it is kp divided by r cube. So that means if we look into the electric field in this particular case, okay, uh, since we have I've already shown it to you, and it's a very simple derivation. If we check the electric field, because of the dipole, we have to resolve the vectors, and the electric field at the equatorial point is nothing but kp divided by r square. So the electric field is not zero, but the potential is zero. So that you have to recall and remember. It has to be a very important and clear. So if we go back to this equatorial line and we check for the axial line, okay, so we can see that on the axis the potential is kp divided by r square or x square. Okay, let's just take the negative sign. I can take it, even if I ignore it, it's fine. So what we have seen here is that the potential on the axis or the axial line, let me write it down as axis, is equal to kp by r square, and the potential on the equatorial line is equal to 0. Now let's imagine a situation where we basically have a charge plus q and minus q, that means the dipole we have it, okay, and we want to find out what is the field at any point p from the dipole. Okay, now this distance that I'm saying, any point p, will always be from the center of the dipole, so I can consider it something like this. Okay, so that means you are basically going to have an angle theta. So this point p makes an angle theta with, or if you draw a straight line joining p and the center of the dipole, you're going to see it makes an angle theta. Now at this particular point p, what will be the potential? That's the question. Okay, so it's obviously not a vector, the potential is not a vector, but we can resolve the direction into two regions, right? One would be obviously the cos component, so let's say that's your the cos theta component, and one will be the vertical component, which is the sin theta component. Okay, now vertical means on the equatorial line. Okay, so that means we can simply write it down, the sin theta component will be 0, because the potential on the equatorial line, this is exactly on the bisector, is going to be 0. Okay, but cos theta component won't be equal to 0. That means the potential will be because of the cos theta component. So a very easy way to remember this is, now the potential at point P, which makes an angle theta with the axis, okay, is equal to nothing but kp by, let's say this distance is r or x or whatever. Okay, let's say this is r square into cos theta, only for the axis, and for this it will be 0. Okay, so this particular component is axis or on the axial line, only the cos component, and on the equatorial line, that's the sine component, which is to be 0 from our previous derivation. So that means this potential at P making an angle theta is nothing but kp cos of theta divided by r square. So it's very important. So let's say they have given you what is the angle, you can definitely put in the angle and find out what is the potential there. Okay, you can check also here. Okay, if this theta is equal to 0 degree, right? 0 degree means it was here, I will take it like this now. If this is like this, then theta would be nothing but 0 degree, right? It was here making an angle, so I slowly reduce that angle and make it 0. So if theta is 0, this VP at 0 degree means it will be on the axis, is equal to nothing but Kp cos of 0 divided by r square, and cos 0 is nothing but 1, so it is Kp by r square. That was the answer for axial line, right? And now if theta is equal to 90 degree, okay, that means we are talking about the field on the equatorial line. Cos 90 is 0, so this is 0, this is 0. So that's why it's perfectly valid. So that means one more formula that you should remember, or rather you can remember only this formula, and then you decide whether it is on the axial line or on the equatorial line. You have to remember this formula, very important. Put theta and 0, 90 and 0 accordingly, depending on whether you want to find out the potential on on the axial line or on the equatorial line. Okay, so I'll give you one task here. Okay, very important, but you can consider this. Find electric field in this case.